Welcome back to the Deep Dive. Today, we're taking a plunge into something really foundational to modern AI, TensorFlow.
Yeah, it's huge.
It really is. And it's
Sure.
far more than just, a coding library. It's Google's incredibly powerful open source platform. It's kind of underpinning so much of what we see in machine learning today.
Exactly.
Our mission here is to, well, cut through the complexity, the jargon, and give you a really crystal clear understanding of what TensorFlow actually is, how it works, and honestly, why it's so pivotal, so key in shaping the future of tech.
Think of this as like your shortcut to truly understanding the machinery behind AI, without getting totally bogged down in every single technical detail.
Right.
We're going to unpack its core components, peek inside how it learns, and even discover exactly where it pops up in the real world. Get ready for some aha moments, hopefully.
Definitely hope so.
Yeah.
So let's really try and peel back the layers here. When we first hear TensorFlow, I think a lot of us just picture that coding library, but it's clearly way more than that, isn't
Oh,
it?
much more.
It's described not just as a library, but, well, a complete open source platform, like a whole ecosystem of flexible tools and community resources.
That's the key word, ecosystem.
Yeah.
It quite literally supports the entire machine learning lifecycle.
This concept of an end-to-end philosophy, that sounds really central to it.
It is. It's fascinating, actually. It means TensorFlow provides integrated tools for every single stage of an ML project. Seriously, everything.
Like from the very beginning.
Yeah, from getting your data in, preparing it, then model training, evaluation, all the way through to actually putting it into production and, keeping an eye on it afterwards, the ongoing monitoring.
Wow.
It's designed to be this comprehensive, kind of streamlined approach.
So it really guides you through the process. It almost sounds like a prescribed workflow. Does that ever feel too rigid, though? Like, does it limit creativity if you're a developer trying to push the boundaries?
That's a fair question.
Yeah.
I mean, for cutting-edge research, yeah, some might find the high-level APIs maybe a bit restrictive. But honestly, for most applications, that guided path is a massive accelerator. You might start building a model using the really intuitive Keras API.
Well, we'll get to Keras.
Then you can seamlessly transition to TensorBoard for monitoring your progress. You need pre-trained models. TensorFlow is right there. And for deployment, you've got dedicated options like TFX, TensorFlow Serving, or litter-T.
So it all fits together.
Exactly. It's a deliberately cohesive workflow.
So this isn't just about making things convenient, is it? It sounds like investing your time and resources into TensorFlow becomes a pretty big strategic decision for a company.
Absolutely. You've hit the nail on the head. Think of it as a very sticky ecosystem.
Sticky.
Yeah, sticky. Once your entire machine learning pipeline,
Yeah.
from data prep to deployment and monitoring, is built on TensorFlow, the cost and complexity of trying to switch to something else, it becomes incredibly high.
Ah, I see. Lock in almost.
Well, yeah, or maybe a powerful incentive for long-term commitment. It's often seen as a strategic advantage for Google's platform adoption,
Right. Okay, so if we look at this ecosystem, maybe just glance across the key parts. What are these components actually doing? Let's start with, say, development and training.
Sure.
We have core TensorFlow itself. That's the fundamental APIs, numerical stuff, automatic differentiation, which is huge, and hardware acceleration, right? GPUs, TPU.
Yep. Yeah, sure.
Then there's Keras, or TF.Keras. That's the high-level, user-friendly API people often start with for building deep learning models fast.
Super popular for that reason.
And TensorFlow datasets that just helps you get data ready, load it, pre-process it.
Exactly. Simplifies that whole initial step. Lots of standard data sets ready to go.
Okay, what about deployment and serving then? Getting it out there.
Right. So you've got TensorFlow Serving. That's for like high-performance serving in production environments. Real heavy-duty stuff.
Okay.
Then there's litter-T. You might remember it as TensorFlow Lite. That's a lightweight library, really optimized for low latency and small size. Think mobile, embedded systems, IoT devices.
Resource-constrained places.
Precisely. And bringing ML straight to the web, there's TensorFlow.js. It's a JavaScript library. Lets you train and deploy models right in browsers or Node.js environments.
Very cool. And for analysis and monitoring, the go-to is TensorBoard, you mentioned.
Oh yeah, TensorBoard is indispensable. It's this incredible suite of visualization tools. Honestly, it's the primary tool for understanding, debugging, optimizing your TensorFlow programs.
We'll definitely need to dig into that more. Finally, these extended tools for production and reusability. TFX, TensorFlow Extended.
Right, TFX. That's a whole end-to-end platform specifically for production ML pipelines. Covers everything from data validation, feature engineering, model management, the real MLOs stuff.
Gotcha. And TensorFlow Hub.
That's the central repository like a library for sharing and reusing pre-trained model components. It's a massive deal for transfer learning, saves a ton of time and data.
Okay, quite an ecosystem.
It really is. But okay, here's where we dive into the absolute foundation. At the core of TensorFlow, underpinning all of this, are three fundamental concepts: tensors, variables, and the computational graph.
The foundational trinity.
Exactly. Understanding this is, well, essential if you want to write efficient and effective TensorFlow code.
Let's start with tensors. They're described as the most fundamental unit, right? A multidimensional array, uniform data type. The primary data structure for all data.
That's it. Conceptually, you can think of them a bit like NumPy arrays, if you're familiar with those.
Okay, yeah.
But with a really crucial difference. They're specifically optimized for high-performance computation on specialized hardware GPUs, TPUs.
So built for speed.
Built for speed. And in the context of that computational graph we mentioned, tensors are the edges. They represent the data that flows between the operations, the nodes.
Now, you mentioned something, or the notes mentioned something
Yep.
really important about tensors, their immutability.
Yes, that's key.
Once a tensor is created, its contents cannot be changed. If you need to modify a value, you actually have to create a whole new tensor.
That's exactly right. Sounds weird at first, maybe, but it has benefits for parallelism and tracking computations.
Huh. And every tensor has three key properties.
Yep. Its rank,
Yeah.
the number of dimensions. So a single number, a scalar, is rank 0. A list of numbers, a vector, is rank 1. A grid, a matrix, is rank 2, and so on.
Okay.
Then it's shape. That's just a tuple describing the size along each dimension, like how many rows and columns in a matrix.
Right.
And finally, it's data type, or D-type. Things like float32 for decimals, int32 for integers. So tf.constant 5.0 is a rank 0 tensor, a scalar. tf.constant 1.0, mu.0, 3.0 is a rank 1 tensor, a vector.
Okay, I'm trying to get my head around this immutability thing. If tensors can't change, how do models actually learn? Like, during training, don't the model's internal settings, its parameters, need to evolve? They can't be fixed, surely.
That's a brilliant question. You've absolutely hit on the crucial point. This is precisely why we have variables. While tensors are fixed, immutable, machine learning models absolutely need mutable state. Things that can change. That's the whole job of TF variable.
Okay.
These are special tensor-like objects. They represent shared, persistent, and mutable state within your TensorFlow program. Their main job. Holding and updating a model's trainable parameters.
The weights and biases.
Exactly. The weights and biases, as the model learns from the data.
So, unlike regular tensors, a variable's value can be changed. You mentioned using something like an assign method.
That's the common way, yeah. But in most operations, they act just like tensors. You can add them, multiply them, etc.
Okay, so we have tensors for data flowing through and variables for the state that needs to change. How do these pieces actually, work together to do the calculations?
Right. That brings us perfectly to the third crucial element, the computational graph.
The blueprint you mentioned.
Exactly. It's a data structure, but basically a network of nodes and edges that represents a series of mathematical computations. The nodes are the operations think, addition, matrix multiplication, things like that, tf.operation.
Well, my edges.
The edges are the tensors that flow between these operations. Data flows in, gets operated on, flows out as another tensor.
Now, I remember hearing that in earlier versions of TensorFlow, like 1.x, you had to manually define this whole static graph before you could even run anything. That sounds painful.
Oh, it could be. It really could. He was often pretty unintuitive, and debugging it was tricky, to say the least.
I'd bet.
That's where TensorFlow 2.x was a genuine revolution. It adopted eager execution by default.
Eager execution.
Yeah. It means operations are executed immediately, right when they're called in your Python code. They return concrete values right away, just like regular Python.
Wow, more intuitive.
Much more. It gives you a way more flexible Pythonic programming experience. Debugging becomes vastly simpler because you can just print things out, step through code like normal.
Okay, but hang on. If eager execution is so much easier for development, why do we still hear about graph execution? Why is it important for, say, production? Is it just about speed?
It's more than just raw speed, although speed is definitely a big part of it. Graph execution offers some really significant advantages, especially crucial for production environments.
Like what?
Well, first, performance optimization. The graph itself, that blueprint, can be analyzed and heavily optimized by the TensorFlow compiler.
How so?
It can do clever things like constant folding, calculating parts ahead of time if they don't change.
Mm.
It can eliminate common sub-expressions. You don't calculate the same thing twice. And it can figure out how to intelligently parallelize computations across multiple hardware units, like all the cores on a GPU or across multiple TPUs.
Okay, so smarter execution.
Much smarter. Second big advantage, portability. A saved graph is a self-contained language-agnostic representation of your model's computation, meaning you can export it and run it in environments without needing a Python interpreter at all. Think running it on mobile devices inside web browsers or on large-scale serving infrastructure. It's completely self-contained.
Right. So it really sounds like that classic trade-off, ease of development with eager execution versus the performance and portability you get from graphs in production. How does TensorFlow, bridge that gap? It seems like you'd want both.
And you can have both. This is where the @tf.function decorator comes in. It's a really elegant solution.
A decorator, like in Python.
Exactly like a Python decorator. It essentially offers the best of both worlds. You write your code in that simple, easy-to-debug, eager style.
Okay.
Then, by just adding @tf.function on top of a Python function, you tell TensorFlow, hey, trace this code.
Trace it?
Yeah. During tracing, TensorFlow's autograph library automatically converts your Python logic loops, conditionals, everything into a highly optimized and portable computational graph behind the scenes.
Wow. So it builds the graph for you from your eager code.
Precisely. It's a fantastic solution that really resolved that historical tension. Makes TensorFlow incredibly versatile, easy to develop, powerful in production.
Okay, that makes a lot of sense. Now that we have the foundations, tensors, variables, graphs, eager versus graph execution, let's talk about actually building neural networks. TensorFlow makes this way simpler through Keras, right? That high-level API, tf.keras.
Absolutely. Keras provides a much more intuitive and straightforward workflow. A great way to see this is with the classic hello world of deep learning, classifying handwritten digits from the MNIST dataset.
Right, MES. So step one is always getting the data ready, data loading and pre-processing.
Yep, you load the MNIST dataset using tf.keras.datasets.mnist.load data. That gives you these 28 by 28 pixel grayscale images. Pixel values go from 0 to 255.
And then the crucial step is normalization.
Crucial. You scale those pixel values down to a 0 to 1 range, usually just by dividing by 255.0.
Why is that so important?
It's pretty much essential for gradient-based optimization to work well. It helps keep the numbers in a manageable range for the learning algorithms, prevents things from blowing up.
Okay, got it. Then model definition. Keras has this sequential API.
Yeah, tf.keras.models. Sequential. It's great for simple linear stacks of layers, one after the other. Very easy to use.
So you might start with tf.keras.layers.flatten, taking that 2D image.
What, takes the 28 by 28 image and just squashes it into a flat 1D array of 784 pixels.
Which you need for the next layers, the dense ones.
Exactly. You need that flat vector for standard fully connected or dense layers. But it's important to remember, like you said, flatten does destroy the spatial information. The network loses track of which pixels were next to each other.
Okay. So after flatten, you add tf.keras.layers dense, say 128 neurons, maybe with a ReLU activation function.
Yep, real use a very common choice.
Yeah.
Good default. Then you might add tf.keras.layers, dropout.
Dropout. That sounds like it's getting rid of things.
It kind of is, temporarily. It's a regularization technique. Say you set a rate of 0.2 during training, it randomly sets 20% of the input units to 0 for each training step.
Why would you do that?
To prevent overfitting. It forces the network to learn more robust features, makes it less reliant on any single neuron. It's like forcing it to have backup plans.
Interesting. And the final layer, usually another dense layer.
Right. For MNIST, you'd have a final dense layer with 10 neurons, one for each digit class, 0 through 9.
And the activation there.
Often for classification, you actually leave the activation off on the very last layer. It outputs what are called logits.
Logits?
Yeah, think of them as the model's raw, unnormalized scores or votes for each class. Keeping them raw like this, without squashing them into probabilities yet, often helps with numerical stability when you pair it with the right loss function during compilation.
Okay, compilation, that's the next step, right? Modeled.compile.
Exactly. Here's where you tell Keras how to learn.
You need an optimizer, like Atom. That seems popular.
Atom is a great go-to. It's an adaptive algorithm, meaning it adjusts the learning rate for different weights as it goes, often leads to faster convergence.
And a loss function. For this kind of problem, sparse categorical cross-entropy.
Perfect. tf.keras.losses. Sparse categorical cross-entropy. That's used for multi-class classification when your labels are just integers, 0, 1, 2, 9. And importantly, you tell it from male objects. True. because our last layer is outputting those raw logits.
Right, connects back. And you also specify metrics to watch during training, like accuracy.
Yeah, accuracy is the obvious one here. Just measures the fraction of images classified correctly.
Okay, compiled, then you train it with model.fit.
Yep. You pass in your training data and labels and tell it how many epochs to run for. An epoch is one full pass through the entire training dataset, maybe 5 epochs for MNIST.
And finally, you evaluate with model.evaluate on the test set. Data it hasn't seen before.
Crucial step. Checks how well the model generalizes. And for this simple setup on MNIST, you should actually get pretty good results, maybe around 98% accuracy.
Wow, 98% just like that. Impressive.
It shows how powerful even basic neural nets can be on the right problem.
Now, you mentioned monitoring progress, but training these deep learning models, it can often feel like you're just staring into a black box, right? You hit train and hope for the best. How do you actually know what's happening inside? Is it learning? Something broken?
That is such a common feeling, and that's exactly where TensorBoard comes in. It's TensorFlow's really powerful suite of visualization tools. Honestly, it's the primary tool you'll use for understanding, debugging, and optimizing your TensorFlow programs.
So it shines a light inside the box.
Totally. It's like flipping on the lights in a dark room. I remember once pulling my hair out for days on this one model that just refused to learn properly. Fired up TensorBoard, and boom, vanishing gradients, clear as day on the charts. It's an absolute lifesaver sometimes.
Okay, so what kind of things can you actually see in TensorBoard?
A whole bunch of useful stuff. Key features include metric tracking. So you can visualize scalars, like your training loss going down and your accuracy going up over time. Super crucial for spotting overfitting or if training stalls.
Right.
You get model graph visualization, so you can actually inspect the model's architecture,
Okay.
see how the layers are connected, make sure you didn't mess something up.
That sounds handy for complex models.
Definitely.
Yeah.
Then there's parameter inspection. You can view histograms and distributions of the weights and biases in your layers as they change during training. This is great for diagnosing problems like vanishing or exploding gradients. You can literally see the weights getting stuck near zero or flying off to infinity.
Wow.
It can even help with profiling your code to find performance bottlenecks. See where the computation is spending most of its time.
And integrating this with Keras sounds easy. You mentioned a callback.
Super simple.
Oh.
Keras has these things called callbacks, which are objects that perform actions at various stages of training. You just use the tf.keras.callbacks, TensorBoard callback. You create a log directory, usually timestamped so runs don't overwrite each other. Instantiate the callback pointing to that directory. TensorBoard callback, tf.keras.callbacks, TensorBoard log dir. Then when you call model.fit, you just pass it in the callbacks list. Model.fit, TensorBoard.fit, callbacks, TensorBoard callback. That's it.
Nice. And launching the dashboard.
Just open your terminal, navigate to the directory above your logs folder, and run TensorBoard logsfit, or whatever your log directory is called. It spins up a local web server.
And what do you see when it opens?
You'll see 7 key tabs. Scalars is probably where you look first plots of your loss and accuracy over training steps or epochs. You watch that loss curve go down.
Hopefully.
Hopefully. The graphs tab gives you that interactive visualization of your model structure. You can zoom in, pan around. And distributions and histograms show how the tensor values, like your weights, are changing over time.
Yeah.
Really useful for spotting those training pathologies, as they call them.
It really does sound like it transforms development from just guesswork into something much more interactive and data-driven. You can see the learning happen.
Exactly. Demystifies the black box, lets you build intuition, and helps you fix problems much faster.
Okay, so while our simple dense network did surprisingly well on MNIST, you mentioned it's not really suited for more complex image tasks. Why do those dense networks fall short when images get more complicated?
2 main reasons, really. First, as we touched on, spatial information loss. When you flatten that image into a long 1D vector for a dense layer, you completely destroy the crucial spatial information, the arrangement of pixels, how they relate to their neighbors. A cat's ear is near its eye for a reason, right? Flattening forgets that.
Right, context is lost.
Completely.
Right.
Second, for larger, more realistic images, you run into a parameter explosion. Imagine a bigger color image. Flattening it creates a huge input vector. Connecting that fully to even a moderately sized dense layer results in an enormous number of weights, meaning your model becomes incredibly slow to train, uses a ton of memory, and is extremely prone to severe overfitting. It just has too many knobs to twiddle, basically.
So that's where convolutional neural networks, CNNs, come in, the standard for computer vision.
Exactly. CNNs are the state-of-the-art architecture. They have a completely different philosophy, really inspired by how the human visual cortex works. It's about hierarchical feature learning.
Hierarchical.
Yeah, the idea is that early layers in the network learn to detect very simple features, maybe horizontal lines, vertical lines, simple curves, basic textures. Then, layers deeper in the network combine these simple features to detect more complex patterns, corners, circles. Deeper still, they combine those to recognize parts of objects, like eyes or wheels, and eventually whole objects.
So building up complexity layer by layer.
Precisely. It's a much more efficient and effective way to process visual information.
And the core building blocks are different too. We have convolutional layers, conv2D.
Right. Instead of connecting every input pixel to every neuron, a conv2D layer uses learnable filters or kernels. Think of them as small windows that slide or convolve across the input image.
What do these filters do?
Each filter is tuned during training to detect a specific visual feature, maybe an edge detector or a texture detector. As it slides across the image, it creates a feature map, indicating where it found that feature. Crucially, this preserves the spatial relationships and uses way fewer parameters than a dense layer because the same filter is reused across the whole image.
Makes sense. You set things like the number of filters, the kernel size.
Yep, kernel size, like 3 by 3 pixels, strides, how many pixels the filter jumps each time, padding, how to handle the edges of the image.
And the other key block is pooling layers, like max pooling 2D.
Right. Pooling layers usually come after convolutional layers. Their job is to downsample the feature map, make it smaller. Max pooling 2D does this by taking the maximum value within a small window, like 2 by 2 pixels, as it slides across.
What's the effect of that?
Two main things. It reduces the spatial dimensions, which cuts down on computation later on, and it helps achieve something called translational invariance.
Meaning, if the feature moves slightly.
Exactly. If the feature the convolutional layer detected shifts slightly in the input image, the max pooling layer is still likely to pick it up. It makes the network more robust to small shifts or distortions in the object's position.
Okay. So for building a CNN, a good next step beyond MNIST might be the CIFAR-10 dataset.
Yeah, CIFAR-10 is a classic benchmark, definitely more challenging than MNIST. It's got 60,000 small 2 by 32 pixel color images across 10 distinct classes, things like airplane, automobile, bird, cat, dog, much more real-world variation.
And the process. Still load and normalize the pixel values 0 to 1.
Yep, that stays the same.
But the model architecture is different.
Right. You typically follow a common pattern. You stack several conv2D and max pooling 2D layers together. This forms the convolutional base, which is responsible for extracting features from the image. The output of this convolutional base, which is usually a set of smaller but deeper feature maps, gets flattened, just like before. And that flattened output is then fed into a classification head, which is usually just a couple of dense layers, like in our MNIST example, to make the final prediction.
And if you look at model.summary for a CNN,
You'll see a clear pattern. As you go deeper through the convolutional base, the height and the width of the feature maps generally decrease because of pooling, but the number of channels or filters tends to increase. The network learns more complex features, represented across more maps.
what's really striking to me is how consistent the Keras API feels, even when we're shifting from a simple dense network to a much more complex CNN. The compile, fit, evaluate steps. They look the same. Is that consistency a deliberate design choice? What's the real benefit?
Oh, it's absolutely deliberate, and it's one of Keras's, superpowers. That consistency vastly simplifies the developer's workflow. You learn the core API, one sequential or the functional API, compile, fit, evaluate, callbacks, and you can apply it across wildly different architectures.
So you don't have to relearn everything just because you switched from processing numbers to processing images.
Exactly. It dramatically flattens the learning curve and lets you focus on the model architecture itself, rather than wrestling with framework specifics. It promotes rapid experimentation.
And the outcome on CFR10, compared to the dense network.
So the CNN will significantly outperform the simple dense network, night and day, really.
Yeah.
It just demonstrates the power of using architectures specifically designed for the type of data you're working with, in this case, images.
Okay, so we've tackled images with CNNs. Let's shift gears again. What about data that comes in sequences, like natural language, sentences, or time series data, like stock prices?
Right. This is where standard dense networks and even CNNs kind of fall short again,
Why is that?
because they process inputs independently. A dense network looks at all input features at once. A CNN looks at local spatial patches. Neither has an inherent mechanism for remembering previous inputs in a sequence.
Right, like trying to understand a sentence one word at a time, but completely forgetting the beginning of the sentence by the time you reach the end. That wouldn't work.
Exactly. You lose all context. That's where recurrent neural networks, RNNs, come to the rescue.
Recurrent, meaning they loop back.
Precisely. RNNs are specialized networks designed for sequential data. They solve the memory problem by introducing loops into their architecture. This allows them to maintain an internal state, or memory, that persists across the elements of the sequence.
How does that work, basically?
The simplest version is the simple RNN layer in Keras, tf.keras.layers.simplerNN. At each step in the sequence, say processing one word, it takes the current input and the output from the previous time step, combines them, and produces an output for the current step. That output is then fed back into the network for the next step. It maintains this hidden state that carries information along the sequence.
Okay, that sounds like it should work, but I feel like there's a catch. Is the simple RNN the whole story?
You're right to be suspicious. There's a critical flaw with the basic simple RNN. It struggles significantly with long sequences.
Why?
It suffers badly from the infamous vanishing gradient problem.
Vanishing gradient. Sounds bad.
It is. During training, the gradients, which tell the network how to update its weights, have to be propagated backwards through time, through that recurrent loop. For long sequences, these gradients can shrink exponentially at each step.
Meaning the updates become tiny.
Exactly. They become so tiny for earlier parts of the sequence that the network effectively stops learning dependencies between elements that are far apart. It's like trying to follow a complex plot in a really long novel. If you kept forgetting the crucial details from the first few chapters, the signal just fades away.
Okay, so the simple loop isn't enough for long-term memory. What's the solution to this vanishing gradient problem? It feels like it needs more than just a tweak.
You're spot on. It wasn't just a tweak. It was a real conceptual breakthrough. Instead of just trying to pass information along passively and hoping it doesn't degrade, the sort of philosophical leap with more advanced RNNs was to give the network explicit control over its own memory.
Control.
Yeah. Imagine if you could consciously decide for every piece of information you encounter, okay, this is important, I need to remember this long term, or this is a relevant detail, I can forget this now, or I need to use this piece of memory to influence my decision right now.
That would be powerful.
Incredibly powerful. That's essentially what these more sophisticated RNN cells do using things called gates.
Gates, like controlling flow.
Exactly. Gates are basically small neural networks within the RNN cell, often with sigmoid activations, which output values between 0 and 1. They learn to carefully control the flow of information, what gets added to the cell's memory, what gets removed or forgotten, and what part of the memory influences the output at the current step. It allows important information to persist over long sequences without vanishing.
That sounds much smarter. And the two most prominent types of these gated architectures are long short-term memory, LSTM, and gated recurrent unit, GRU.
Those are the main ones you'll encounter. tf.keras.layers.
Yeah.
LSTM is kind of the classic solution, been around longer. It's quite complex internally. It maintains a separate cell state vector. You can think of it like a long-term memory conveyor belt, which is carefully managed by 3 gates.
Oh.
An input gate, a forget gate, and an output gate.
Forget gate. So it literally learns what to forget.
Yes. The forget gate learns to discard information from the cell state that's no longer relevant. It's incredibly robust for complex tasks where long-range context is critical.
And the GRU, tf.keras.layers.gru.
The GRU is a more modern, slightly simpler alternative. It combines the forget and input gates into a single update gate and merges the cell state and hidden state. It generally has fewer parameters than an LSTM.
How do they compare in practice?
Often, they perform very comparably. LSTMs might have a slight edge on very complex tasks requiring really long memory, but GRUs are computationally more efficient, faster to train, use less memory. So while simpler NNs are mostly just for teaching purposes due to vanishing gradients, GRUs offer a really good balance of performance and efficiency, and LSTMs are sort of the powerful, robust workhorse.
Okay, let's see this in action. We could apply this to text classification, maybe. Like analyzing movie reviews from IMDb to see if they're positive or negative.
Perfect example. Standard NLP tasks.
So for text, we need some specific preprocessing first, right? You can't just feed raw words in.
Correct. First, you need to convert the text into numbers. A common way is using tf.keras.layers.text vectorization. This layer handles building a vocabulary of unique words from your training data and then converts sentences into sequences of integer indices.
So each word gets a number.
Right. Then, the standard input layer for NLP models is usually tf.keras.layers.embedding. This takes those integer sequences and maps each integer word to a dense, low-dimensional vector.
A vector, like a point in space.
Kind of, yeah. These are called word embeddings. The key thing is that these vectors are learned during training. The network learns to map similar words to similar vectors in this embedding space.
Cool. So after the embedding layer, you'd add your RNN layer, maybe an LSTM or a GRU.
Exactly. You feed the sequence of word embeddings into the recurrent layer.
And I've seen people wrap these layers in something called bidirectional.
Yes. TFIA.Keras.layers.
Yeah.
Bidirectional. That's a common technique, especially for NLP. It essentially creates two separate copies of the RNN layer, say an LSTM. One processes the sequence forwards from start to end, and the other processes it backwards from end to start.
Right backward.
Because sometimes the meaning of a word depends on what comes after it in the sentence, not just what came before. Bidirectional wrappers let the network capture context from both directions. It then usually concatenates the outputs from the forward and backward passes. Often gives a nice performance boost on tasks like sentiment analysis.
So the final model effectively learns to classify the sentiment, positive or negative, by really understanding the sequence and the context of the words in the review.
That's the goal, yeah. It learns which patterns of words and phrases tend to indicate positive or negative feelings.
Okay, this is great. We've covered dense networks, CNNs for vision, RNNs for sequences. Now maybe we can try and bring it all together. A kind of capstone challenge, an
Yeah.
image caption generator.
Ooh, ambitious. But yeah, that's a fantastic project because it truly combines computer vision and natural language processing. You need to understand the image and generate a coherent sentence about it.
How does that work architecturally?
It typically uses what's called an encoder-decoder architecture.
Encoder-decoder, okay.
The encoder part is usually a CNN. Its job is to understand the image. You take a powerful pre-trained CNN, something like Exception, MobileNet, Inception v3, models trained on huge data sets like ImageNet, and you use it as a fixed feature extractor. You basically chop off its final classification layer, the part that would normally predict, say, the 1,000 object classes. The output from the layer just before that gives you a rich, fixed-size vector representation that summarizes the visual content of the image.
So the CNN encodes the image into a vector. What's the decoder?
The decoder is typically an RNN, often an LSTM-based language model. It takes that image feature vector from the encoder as its initial input, or sometimes injects it at each step. Its job is to generate the caption one word at a time.
How does it generate word by word?
At each step, it considers the image features and the words it has generated so far, and then predicts the next most likely word in the sequence.
Fascinating. What about the data pipeline for something like this? You need images and captions.
Yeah, a common data set is Flick 8K or Flick 30K. You have images and multiple human-written captions for each image.
How do you prepare that?
Images need to be resized and pre-processed to match the input requirements of your pre-trained CNN encoder. Captions need cleaning lowercase, remove punctuation. Crucially, you add special start and end tokens to each caption. These tell the decoder when to begin and end the generation process.
Like signaling start and stop.
Exactly. Then you build a vocabulary from all the words in the captions and convert the captions into sequences of integer indices, maybe using Keras tokenizer.
And implementation. Sounds complex.
It has a few key steps. One very important practical trick is feature extraction. Instead of running the potentially large CNN encoder over the same image again and again during decoder training, you first pass all your training images through the pre-trained CNN once and save the resulting feature vectors to disk.
Pre-compute the image features. Saves a ton of time.
A massive amount of computation time during the actual decoder training. Then you build the decoder. This usually requires the Keras functional API, not sequential, because you have multiple inputs. The image features and the sequence of previously generated words, starting with start.
How do they combine?
The image features might go through a dense layer to get them to the right dimension. The word sequence goes through an embedding layer, as we discussed. Then these are typically fed into the LSTM. The LSTM's output predicts the next word, usually via another dense layer with a softmax activation to get probabilities over the whole vocabulary.
And training. How do you teach it to predict the next word?
You need a data generator.
Yeah.
For each image and its caption, like a dog catches a ball, you create input-output pairs. For example,
Right.
input, image features, start, target, cat A. Then input, image features, start A, target.dog. Input, image features, start a dog, catches, and so on, until the target is in. It learns to predict the next word given the image and the preceding words.
And then for inference, generating a caption for a brand new image.
You first extract its features using the same CNN encoder. You initialize the decoder input sequence with just the start token. You feed these into the decoder, get the predicted probabilities for the next word. You usually pick the word with the highest probability, that's called greedy search. You append that predicted word to your sequence. Then you feed the new sequence back into the decoder, predict the next word, append it, and repeat this loop until the decoder predicts the end token or you hit some maximum caption length.
Wow, that really ties everything together. But
Yeah?
this project also sounds like it would expose some real challenges, right? It feels like something that could go wrong in interesting ways.
Oh, absolutely. This kind of project really brings you face to face with some of the real-world hurdles and limitations of current AI. It powerfully highlights that these models, while amazing at sophisticated pattern matching, often lack, well, true understanding, common sense, and robustness.
Like what kind of issues crop up?
Well, one is the semantic gap, sometimes addressed by fine-tuning. The pre-trained CNN encoder was likely trained for image classification on ImageNet. Its goal was just to say dog present. But for captioning, we need a much richer description. A brown dog catching a red frisbee in a park.
The tasks are different.
Very different. The features learned for classification might not be ideal for detailed description. So often you need to fine-tune, meaning you unfreeze some of the later layers of the CNN and train them jointly with the LSTM decoder on your captioning data. This helps the vision part learn features more relevant to description.
Makes sense. What else?
A really common and sometimes funny, sometimes worrying issue is object hallucination and contextual failures.
Hallucination, like the model sees things that aren't there.
Exactly. The model might confidently describe objects or attributes in the caption that simply are not present in the image. Or it might completely miss the actual context or action happening in the scene.
Why does that happen? Is it just guessing?
It happens because the model isn't truly seeing or understanding the image in a human sense. It's learned complex statistical correlations from the training data. It knows that images with dogs often also have grass and maybe a frisbee, so it might insert a frisbee even if there isn't one, just because the dog features are strong. It's matching patterns, not comprehending scenes.
That distinction between pattern matching and understanding seems really crucial.
It's perhaps the central challenge in AI right now.
And how do you even measure if a caption is good? That sounds subjective.
It is highly subjective. And that leads to another big hurdle, the flawed nature of evaluation metrics. The standard metric used is often BLEU, Bilingual Evaluation Understudy, which was actually borrowed from machine translation.
How does BLE work?
It basically measures the overlap of n-grams, sequences of n-words, between the generated caption and one or more human-written reference captions. So it checks if the model used similar short phrases as the humans did.
What's the problem with that?
The big problem is that BLEU cannot assess factual correctness, creativity, or overall semantic meaning. A caption could be factually wrong, a cat chasing a blue ball when it's a dog chasing a red one, but still get a decent BLEU score if it happens to use some common words or phrases found in the reference captions.
Yeah.
Conversely, a perfectly accurate and perhaps more creative or descriptive caption might get a low BLEU score simply because it used different wording than the reference captions. It really highlights how difficult it is to define and computationally measure what makes a caption truly good.
Yeah, that's a tough one. Any other major hurdles?
Definitely dataset and language challenges. Creating large, high-quality image caption datasets is incredibly expensive and labor-intensive. Humans have to write all those captions. And these datasets inevitably contain noise, biases, and reflect the cultural context of the annotators.
And for other languages?
It's a massive hurdle for low-resource languages. If you don't have large-scale datasets like FlickAK or Coco available in, say, Swahili or Welsh, building effective captioning models becomes extremely difficult. It really limits the global accessibility and applicability of this kind of AI.
So building the model is complex, but dealing with these real-world issues, understanding, evaluation, data, that's where the really hard problems lie.
That's often the case, yeah. Training the model can sometimes feel like the easy part in retrospect.
Okay, so we've trained our models, wrestled with the challenges. The final step is actually getting them out into the real world, right? Deployment. TensorFlow offers tools for this too.
Absolutely. Training is only half the battle.
You mentioned TensorFlow Hub earlier for reusing models. Does that help in deployment too?
It helps more in the development phase, accelerating it by enabling transfer learning. You grab a pre-trained model from the hub, often using the simple hub, Keras layer, integrate it into your own model, and fine-tune it. It dramatically reduces the need for massive data sets and computational resources to get good performance. So it speeds up getting to deployment.
Gotcha. But for actually running the model on different devices, we talked about litter-T, formerly TensorFlow Lite, for the edge.
Exactly. Litter-T is specifically designed for deploying models on mobile, embedded, and IoT devices, places where resources like memory, power, and computational capacity are limited.
So its focus is inference on the device.
Yes, high performance, low latency inference right there on the edge device. No need to call out to a server.
How does it make the model suitable for that?
There's a key tool called the TensorFlow Lite Converter. It takes your trained TensorFlow model and optimizes it heavily. It uses techniques like quantization.
Reducing precision.
Right. Converting the model's weights from, say, 32-bit floating point numbers down to 8-bit integers, which drastically reduces model size and speeds up computation on hardware that supports it. And pruning, which intelligently removes weights or connections in the network that don't contribute much to the final output.
Making it smaller and faster.
Exactly. The result is a compact .tflight file. Litter-T is ideal for native mobile apps needing real-time, offline ML think camera effects, on-device speech recognition anywhere. Maximum performance and efficiency on the device itself are paramount.
Okay, so that's edge performance. What about the web? You mentioned TensorFlow.js.
Right. TensorFlow.js targets web browsers and Node.js environments. It's pretty amazing because it lets you define, train, and run models entirely in JavaScript.
Train in JavaScript. Wow.
Yeah. Or, more commonly, convert your Python-trained models to run in JS. The advantages are really compelling for certain use cases. Low latency. Inference happens directly on the client's machine, in their browser. No network round trip to a server, which is great for interactive applications. Enhanced privacy. Since the data stays in the browser, sensitive user data never has to leave their device. That's huge.
Definitely a big plus today.
Also, reduced cost. You don't necessarily need expensive GPU-equipped servers constantly running to handle inference requests. The client's machine does the work. And accessibility and scale. Anyone with a modern web browser can access your ML model with literally zero installation required. Just load the web page.
So ideal use cases might be interactive web demos, adding ML features to existing websites, or those privacy-first applications.
Exactly. Places where maximum accessibility and reaching the widest possible audience are the primary goals.
So what's really fascinating here is that litter-TIS and TensorFlow.js, they aren't really redundant, are they? It sounds like they represent a fundamental strategic choice you have to make when developing a product.
That's a great way to put it. It's often a choice between optimizing for maximum performance on specific, often mobile or embedded hardware, which is where Litter shines, versus optimizing for maximum accessibility and reach via the web, where TensorFlow.js is king.
Understanding that strategic distinction seems absolutely key for planning any real-world deployment.
It really is. You need to think about where your users are, what devices they're using, your performance requirements, privacy concerns, and then choose the right deployment tool from the TensorFlow ecosystem for that specific job.
Wow. What a journey we've taken.
Yeah.
We've really done a deep dive into TensorFlow today. We went from its foundational principles, tensors, variables, graphs, and explored the whole ecosystem.
Yeah, from Keras and TensorBoard
To building complex models like CNNs for vision and RNNs for sequences, understanding the debugging process, facing those really tricky real-world hurdles like hallucination and flawed metrics in the captioning project.
Right, the gap between pattern matching and understanding.
And finally, looking at how to deploy these models into vastly different environments using tools like Hub, Litter-T, and TensorFlow.js.
It really reinforces that getting a handle on TensorFlow gives you access to this incredibly powerful, integrated, and, as we discussed, strategically designed platform. It equips you to tackle almost any ML challenge you might encounter.
It definitely feels that way. So as we wrap up this deep dive, here's maybe a provocative thought for you, our listener, to mull over. While we've seen just how powerful TensorFlow is for building models that get incredibly good at pattern matching.
Like that 98% on MNIST, or classifying images or generating plausible text.
Right. But that capstone project, the image caption generator, it really highlights something deeper, didn't it? That building a model is often the easy part. Building one that is robust, reliable, and truly understands the world, well, that's the real frontier of research. So what does that mean for how you approach learning and building with AI? When you use these tools, what stands out to you about that crucial, maybe fuzzy, line between sophisticated statistical pattern matching and genuine understanding? Something to think about.